Section 34 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Ielmie. Calculus Made Easy by Silvanus P. Thompson. Chapter 15. How to Deal with Sines and Cosines, Part 2. Second differential coefficient of sine or cosine. We have seen that when sine theta is differentiated with respect to theta, it becomes cos theta, and that when cos theta is differentiated with respect to theta, it becomes minus sine theta, or, in symbols, d squared of sine theta over d theta squared is equal to minus sine theta. So we have this curious result that we have found a function such that if we differentiate it twice over, we get the same thing from which we started, but with the sign changed from plus to minus. The same thing is true for the cosine. For differentiating cos theta gives us minus sine theta, and differentiating minus sine theta gives us minus cos theta, or thus d squared cos theta over d theta squared is equal to minus cos theta. Sines and cosines are the only functions of which the second differential coefficient is equal and of opposite sign to the original function. Examples. With what we have so far learned, we can now differentiate expressions of a more complex nature. 1. Y is equal to arc sine x. If y is the arc whose sine is x, then x equals sine y. dx over dy is equal to cos y. Passing now from the inverse function to the original one, we get dy over dx is equal to 1 over dx over dy, which is equal to 1 over cos y. Now, cos y is equal to 1 minus the square root of 1 minus sine squared y, which is equal to the square root of 1 minus x squared. Hence, dy over dx is equal to 1 over square root of 1 minus x squared. A rather unexpected result. 2. Y is equal to cos cubed theta. This is the same as y is equal to cos theta cubed. Let cos theta be equal to v, then y be equal to v cubed. dy over dv is 3v squared. dv over d theta is equal to minus sine theta, and dy over d theta is equal to dy over dv times dv over d theta, which is equal to minus 3 cos squared theta sine theta. 3. Y is equal to sine brackets x plus a close brackets. Let x plus a be equal to v, then y is equal to sine of v. dy over dv is equal to cos v. dv over dx is equal to 1, and dy over dx is equal to cos of open brackets x plus a close brackets. 4. Y is equal to log base e of sine theta. Let sine theta be equal to v, y equal to log base e of v, then dy over dv is equal to 1 over v, and dv over d theta is equal to cos theta. dy over d theta is equal to 1 over sine theta times cos theta, which is equal to cotangent of theta. 5. Y is equal to cotangent of theta, which is equal to cos theta over sine theta. dy over d theta is equal to minus sine squared theta minus cos squared theta divided by sine squared theta is equal to minus, open brackets, 1 plus cot squared theta, close brackets, which is equal to minus cosecant squared theta. 6. Y is equal to tan 3 theta. Let 3 theta be equal to v, y be equal to tan v, and dy over dv be equal to secant square of v. dv over d theta is equal to 3. dy over d theta is equal to 3 secant squared of 3 theta. 7. Y is equal to square root of 1 plus 3 tan squared of theta. Y is equal to 1 plus 3 tan squared theta in brackets to the power of 1/2. Let 3 tan squared theta be equal to v. Y is equal to, open brackets, 1 plus v, close brackets, to the power of 1/2. dy over dv is equal to 1 over 2 square root of 1 plus v. See page 67. dv over d theta is equal to 6 tan theta secant squared theta. For if tan theta is equal to u, v is equal to 3u squared, dv over du is equal to 6u, du over d theta is equal to secant squared of theta. Hence, dv over d theta is equal to 6, open brackets, tan theta secant squared theta, close brackets. Hence, dy over d theta is equal to 6 tan theta secant squared theta over 2 times the square root of 1 plus 3 tan squared theta. 8. Y is equal to sine x cos x. dy over dx is equal to sine x times minus sine x plus cos x times cos x, which is equal to cos squared x minus sine squared x. End of section 34. Recording by Ielmie.
Section 35 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 35. Exercises 14. 1. Differentiate the following. 1. Y equal a sine of the quantity theta minus pi over 2. 2. Y equal sine squared theta and y equal sine 2 theta. 3. Y equal sine cubed of theta and y equal sine of 3 theta. Answer. 1. dy over d theta equals a cosine of the quantity theta minus pi over 2. 2. dy over d theta equals 2 sine of theta cosine of theta equals sine of 2 theta and dy over d theta equal 2 cosine 2 theta. 3. dy over d theta equal 3 sine squared theta cosine theta and dy over d theta equal 3 cosine 3 theta. 2. Find the value of theta for which sine theta times cosine theta is a maximum. Answer. Theta equals 45 degrees, or pi over 4 radians. 3. Differentiate y equal 1 over 2 pi times cosine 2 pi nt. Answer. dy over dt equal negative n sine 2 pi nt. 4. If y equal sine a to the x power, find dy over dx. Answer. A to the x power log base epsilon of a cosine a to the x power. 5. Differentiate y equal log to base epsilon of cosine x. Answer. Cosine x over sine x equal cotan x. 6. Differentiate y equal 18.2 sine of the quantity x plus 26 degrees. Answer. 18.2 cosine of the quantity x plus 26 degrees. 7. Plot the curve y equal 100 sine of the quantity theta minus 15 degrees and show that the slope of the curve at theta equals 75 degrees is half the maximum slope. Answer. The slope is dy over d theta equal 100 cosine of the quantity theta minus 15 degrees, which is a maximum when the quantity theta minus 15 degrees equals 0 or theta equals 15 degrees. The value of the slope being then equal 100. When theta equals 75 degrees, the slope is 100 cosine the quantity 75 degrees minus 15 degrees equals 100 cosine of 60 degrees equals 100 times 1/2 equal 50. 8. If y equals sine theta times sine 2 theta, find dy over d theta. Answer: cosine theta sine 2 theta plus 2 cosine 2 theta sine theta equals 2 sine theta of the quantity cosine squared theta plus cosine 2 theta equals 2 sine theta of the quantity 3 cosine squared theta minus 1. 9. If y equal a times the tangent to the m power of theta to the n power, find the differential coefficient of y with respect to theta. Answer: amn theta to the n minus 1 power, tangent to the m minus 1 power of theta to the n power, secant squared theta to the n power. 10. Differentiate y equal epsilon to the x power sine squared of x. Answer: epsilon to the x power times the quantity sine squared x plus sine 2x, epsilon to the x power times the quantity sine squared x plus 2 sine 2x plus 2 cosine 2x. 11. Differentiate the three equations of exercises 13, number 4, and compare their differential coefficients as to whether they are equal or nearly equal for very small values of x, or for very large values of x, or for values of x in the neighborhood of x equal 30. Answers: 1. dy over dx equal ab over the quantity squared x plus b. 2. a over b times epsilon to the negative x over b power. 3. 1 over 90 degrees times ab over the quantity b squared plus x squared. 12. Differentiate the following. 1. Y equal secant x. 2. Y equal arc cosine x. 3. Y equal arctangent x. 4. Y equal arcsecant x. 5. Y equal tangent x times the square root of 3 secant x. Answers. 1. dy over dx equal secant x tangent x. 2. dy over dx equal negative 1 over the square root of 1 minus x squared. 3. dy over dx equal 1 over 1 plus x squared. 4. dy over dx equal 1 over x times the square root of x squared minus 1. 5. dy over dx equal the square root of 3 secant x times the quantity 3 secant squared x minus 1 all over 2. 13. Differentiate y equals sine of the quantity to the 2.3 power of 2 theta plus 3. Answer. dy over d theta equals 4.6 times the quantity to the 1.3 power of 2 theta plus 3, cosine of the quantity to the 2.3 power of 2 theta plus 3. 14. Differentiate y equal theta cubed plus 3 sine of the quantity theta plus 3 minus 3 to the sine theta power minus 3 to the theta power. Answer. dy over d theta equals 3 theta squared plus 3 cosine of the quantity theta plus 3 minus log base epsilon of 3 times the quantity cosine theta times 3 to the sine theta power plus 3 theta. 15. Find the maximum or minimum of y equal theta cosine theta. Answer. Theta equals cotangent theta. Theta equals plus or minus 0.86 is maximum for positive theta, minimum for negative theta. End of section 35.
Section 36 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 16, Partial Differentiation, Part 1. We sometimes come across quantities that are functions of more than one independent variable. Thus, we may find a case where y depends on two other variable quantities, one of which we will call u and the other v. In symbols, y equals f open brackets u, v close brackets. Take the simplest concrete case. Let y equals u times v. What are we to do? If we were to treat v as a constant and differentiate with respect to u, we should get dy subscript v equals v du, or if we treat u as a constant and differentiate with respect to v, we should have dy subscript u equals u dv. The little letters here put as subscripts are to show which quantity has been taken as constant in the operation. Another way of indicating that the differentiation has been performed only partially, that is, has been performed only with respect to one of the independent variables, is to write the differential coefficients with Greek deltas, like delta instead of little d. In this way, delta y over delta u equals v, and delta y over delta v equals u. If we put in these values for v and u respectively, we shall have dy subscript v equals delta y over delta u du, and dy subscript u equals delta y over delta v dv, which are partial differentials. But if you think of it, you will observe that the total variation of y depends on both these things at the same time. That is to say, if both are varying, the real dy ought to be written dy equals delta y over delta u du add delta y over delta v dv, and this is called a total differential. In some books it is written dy equals open brackets dy over du close brackets du add open brackets dy over dv close brackets dv. Example 1. Find the partial differential coefficients of the expression w equals 2ax squared add 3bxy add 4cy cubed. The answers are delta w over delta x equals 4ax add 3by, and delta w over delta y equals 3bx add 12cy squared. The first is obtained by supposing y constant, the second is obtained by supposing x constant. Then dw equals open brackets 4ax add 3by close brackets dx add open brackets 3bx add 12cy squared close brackets dy. Example 2. Let z equals x to the power of y. Then, treating first y and then x as constant, we get in the usual way delta z over delta x equals y times x to the power of y minus 1, and delta z over delta y equals x to the power of y times log base ex, so that dz equals y times x to the power of y minus 1 dx add x to the power of y log base ex dy. Example 3. A cone having height h and radius of base r has volume v equals 1/3 pi r squared h. If its height remains constant, while r changes, the ratio of change of volume with respect to radius is different from the ratio of change of volume with respect to height which would occur if the height were varied and the radius kept constant, for delta v over delta r equals 2 pi over 3 rh. Delta v over delta h equals pi over 3 r squared. The variation when both the radius and the height change is given by dv equals 2 pi over 3 times rh dr, add pi over 3 times r squared dh. Example 4. In the following example, big F and little f denote two arbitrary functions of any form whatsoever. For example, they may be sine functions, or exponentials, or mere algebraic functions of the two independent variables t and x. This being understood, let us take the expression y equals big F open brackets x add at close brackets add little f open brackets x minus at close brackets, or y equals big F as a function of w add little f as a function of v, where w equals x add at and v equals x minus at. Then delta y over delta x equals delta big F as a function of w over delta w times delta w over delta x add delta little f as a function of v over delta v times delta v over delta x equals big F as a function of w prime times 1 add little f as a function of v prime times 1, where the figure 1 is simply the coefficient of x in w and v, and delta squared y over delta x squared equals big F as a function of w double primed add little f as a function of v double primed. Also, delta y over delta t equals delta big F as a function of w over delta w times delta w over delta t add delta little f as a function of v over delta v times delta v over delta t equals big F as a function of w primed times a minus little f as a function of v primed times a, and delta squared y over delta t squared equals big F as a function of w double primed times a squared add little f as a function of v double primed times a squared, whence delta squared y over delta t squared equals a squared delta squared y over delta x squared. This differential equation is of immense importance in mathematical physics. End of section 36. Section 37 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 16, Partial Differentiation, Part 2. Maxima and minima of functions of two independent variables. Example 5. Let us take up again exercise 9, page 107, number 4. Let x and y be the length of two of the portions of the string. The third is 30 minus, open brackets, x add y, close brackets, and the area of the triangle is a equals the square root of s, open brackets, s minus x, close brackets, open brackets, s minus y, close brackets, open brackets, s minus 30 plus x plus y, close brackets, where s is the half perimeter, 15, so that a equals the square root of 15p, where p equals, open brackets, 15 minus x, close brackets, open brackets, 15 minus y, close brackets, open brackets, x add y minus 15, close brackets, equals xy squared add x squared y minus 15x squared minus 15y squared minus 45xy add 450x add 450y minus 3375. Clearly A is maximum when P is maximum. dP equals delta P over delta x dx add delta P over delta y dy. For a maximum, clearly it will not be a minimum in this case, one must have simultaneously delta P over delta x equals 0 and delta P over delta y equals 0. That is, 2xy minus 30x add y squared minus 45y add 450 equals 0, and 2xy minus 30y add x squared minus 45x add 450 equals 0. An immediate solution is x equals y. If we now introduce this condition in the value of p, we find p equals open brackets 15 minus x close brackets squared open brackets 2x minus 15 close brackets equals 2x cubed minus 75x squared add 900x minus 3375. For maximum or minimum, dp over dx equals 6x squared minus 150x add 900 equals 0, which gives x equals 15 or x equals 10. Clearly x equals 15 gives the minimum area, x equals 10 gives the maximum, for d2p over dx squared equals 12x minus 150, which is plus 30 for x equals 15 and minus 30 for x equals 10. Example 6. Find the dimensions of an ordinary railway coal truck with rectangular ends so that for a given volume V, the area of sides and floor together is as small as possible. The truck is a rectangular box open at the top. Let x be the length and y the width, and the depth is v over xy. The surface area is S equals xy add 2v over x add 2v over y. ds equals delta s over delta x dx add delta s over delta y dy equals open brackets y minus 2v over x squared close brackets dx add open brackets x minus 2v over y squared close brackets dy. For minimum, clearly it won't be a maximum here. Y minus 2v over x squared equals 0. X minus 2v over y squared equals 0. Here also, an immediate solution is x equals y, so that s equals x squared plus 4v over x. ds over dx equals 2x minus 4v over x squared equals 0 for minimum, and x equals the cube root of 2v. End of section 37. Section 38 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 38. Exercises 15. 1. Differentiate the expression x cubed over 3 minus 2x cubed y minus 2y squared x add y over 3 with respect to x alone and with respect to y alone. Answer. X squared minus 6x squared y minus 2y squared. 1/3 minus 2x cubed minus 4xy. 2. Find the partial differential coefficients with respect to x, y and z of the expression x squared yz plus xy squared z plus xyz squared plus x squared y squared z squared. Answer. 2xyz add y squared z add z squared y add 2xy squared z squared. 2xyz add x squared z add x z squared add 2x squared y z squared. 2xyz add x squared y add x y squared add 2x squared y squared z. 3. Let r squared equals open brackets x minus a close brackets squared add open brackets y minus b close brackets squared add open brackets, z minus c, close brackets, squared. Find the value of delta r over delta x, add delta r over delta y, add delta r over delta z. Also find the value of delta squared r over delta x squared, add delta squared r over delta y squared, add delta squared r over delta z squared. Answer: 1 over r, open brackets, x minus a, close brackets, add, open brackets, y minus b, close brackets, add, open brackets, z minus c, close brackets, equals, open brackets, x add y add z, close brackets, minus, open brackets, a add b add c, close brackets, all over r. 3 over r. 4. Find the total differential of y equals u to the power of v. Answer: dy equals v u to the power of v minus 1 du, add u to the power of v log base e u dv. 5. Find the total differential of y equals u cubed sin v of y equals, open brackets, sin x, close brackets, to the power of u, and of y equals log base e u all over v. Answer: dy equals 3 sin v u squared du, add u cubed cos v dv. dy equals u sin x to the power of u minus 1 cos x dx, add, open brackets, sin x, close brackets, to the power of u log base e sin x du. dy equals 1 over v times 1 over u du minus log base e u times 1 over v squared dv. 6. Verify that the sum of three quantities x, y, z, whose product is a constant k, is maximum when these three quantities are equal. 7. Find the maximum or minimum of the function u equals x add 2xy add y. Answer: minimum for x equals y equals minus a half. 8. The Post Office regulations state that no parcel is to be of such a size that its length plus its girth exceeds 6 feet. What is the greatest volume that can be sent by post? A. In the case of a package of rectangular cross-section. B. In the case of a package of circular cross-section. Answer: A. Length 2 feet, width equals depth equals 1 foot. Volume equals 2 cubic feet. B. Radius equals 2 over pi feet equals 7.46 inches. Length equals 2 feet. Volume equals 2.54. 9. Divide pi into 3 parts such that the continued product of their signs may be a maximum or minimum. Answer: all 3 parts equal, the product is maximum. 10. Find the maximum or minimum of u equals e to the power of x add y all over xy. Answer: minimum for x equals y equals 1. 11. Find the maximum and minimum of u equals y add 2x minus 2 log base ey minus log base ex. Answer: minimum, x equals a half and y equals 2. 12. A Telfordge bucket of given capacity has the shape of a horizontal isosceles triangular prism, with the apex underneath and the opposite face open. Find its dimensions in order that the least amount of iron sheet may be used in its construction. Answer: angle at apex equals 90 degrees. Equal sides equals length equals the cube root of 2v. End of section 38.
Section 39 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 17, Integration, Part 1. The great secret has already been revealed that this mysterious symbol, the integral sign, which is, after all, only a long S, merely means the sum of, or the sum of all such quantities as. It therefore resembles that other symbol, the Greek sigma, which is also a sign of summation. There is this difference, however, in the practice of mathematical men as to the use of these signs, that while sigma is generally used to indicate the sum of a number of finite quantities, the integral sign is generally used to indicate the summing up of a vast number of small quantities, of indefinitely minute magnitude, mere elements, in fact, that go to make up the total required. Thus, integral dy equals y, and integral dx equals x. Anyone can understand how the whole of anything can be conceived of as made up of a lot of little bits, and the smaller the bits, the more of them there will be. Thus, a line 1 inch long may be conceived as made up of 10 pieces, each 1/10 of an inch long, or of 100 parts, each part being 1/100th of an inch long, or of 1,000,000 parts, each of which is 1/1,000,000th of an inch long. Or, pushing the thought to the limits of conceivability, it may be regarded as made up of an infinite number of elements, each of which is infinitesimally small. Yes, you will say, but what is the use of thinking of anything that way? Why not think of it straight off, as a whole? The simple reason is that there are a vast number of cases in which one cannot calculate the bigness of the thing as a whole without reckoning up the sum of a lot of small parts. The process of integrating is to enable us to calculate totals that otherwise we should be unable to estimate directly. Let us first take one or two simple cases to familiarize ourselves with this notion of summing up a lot of separate parts. Consider the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus etc. Here, each member of the series is formed by taking it half the value of the preceding. What is the value of the total if we could go on to an infinite number of terms? Every schoolboy knows that the answer is 2. Think of it, if you like, as a line. Begin with 1 inch, add a ½ inch, add a quarter, add an eighth, and so on. If at any point of the operation we stop, there will still be a piece wanting to make up the whole 2 inches, and the piece wanting will always be the same size as the last piece added. Thus, if after having put together 1, 1/2, and 1/4, we stop, there will be 1/4 wanting. If we go on till we have added 1/64th, there will still be 1/64th wanting. The remainder needed will always be equal to the last term added. By an infinite number of operations only should we reach the actual 2 inches. Practically, we should reach it when we got to pieces so small that they could not be drawn. That would be after about 10 terms, for the 11th term is 1/1024th. If we want to go so far that not even a Whitworth's measuring machine would detect it, we should merely have to go to about 20 terms. A microscope would not show even the 18th term. So the infinite number of operations is no such dreadful thing after all. The integral is simply the whole lot. But, as we shall see, there are cases in which the integral calculus enables us to get at the exact total that there would be as the result of an infinite number of operations. In such cases, the integral calculus gives us a rapid and easy way of getting at a result that would otherwise require an interminable lot of elaborate working out. So we had best lose no time in learning how to integrate. End of section 39. Section 40 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 17. Integration, Part 2. Slopes of curves and the curves themselves. Let us make a little preliminary inquiry about the slopes of curves. For we have seen that differentiating a curve means finding an expression for its slope, or for its slopes at different points. Can we perform the reverse process of reconstructing the whole curve if the slope or slopes are prescribed for us? Go back to case 2 on page 82. Here we have the simplest of curves, a sloping line with the equation y equals ax plus b. We know that here b represents the initial height of y when x equals 0, and that a, which is the same as dy over dx, is the slope of the line. The line has a constant slope. All along it, the elementary triangles have the same proportion between height and base. Suppose we were to take the dx's and dy's of finite magnitude so that 10 dx's made up 1 inch. Then there would be 10 little triangles. Now suppose that we were ordered to reconstruct the curve, starting merely from the information that dy over dx equals a. What could we do? Still taking the little d's as of finite size, we could draw 10 of them, all with the same slope, and then put them together end to end, like this. And, as the slope is the same for all, they would join to make, as in figure 48, a sloping line, sloping with the correct slope dy over dx equals a. And whether we take the dy's and dx's as finite or infinitely small, as they are all alike, clearly y over x equals a, if we reckon y as the total of all the dy's, and x as the total of all the dx's. But whereabouts are we to put this sloping line? Are we to start at the origin, uppercase O, or higher up? As the only information we have is as to the slope, we are without any instructions as to the particular height above uppercase O. In fact, the initial height is undetermined. The slope will be the same, whatever the initial height. Let us therefore make a shot at what may be wanted, and start the sloping line at a height uppercase C above uppercase O. That is, we have the equation y equals ax plus uppercase C. It becomes evident now that in this case the added constant means a particular value that y has when x equals 0. Now let us take a harder case, that of a line the slope of which is not constant, but turns up more and more. Let us assume that the upward slope gets greater and greater in proportion as x grows. In symbols, this is dy over dx equals ax. Or, to give a concrete case, take a equals 1/5, so that dy over dx equals 1/5 x. Then we had best begin by calculating a few of the values of the slope at different values of x, and also draw little diagrams of them. When x equals 0, dy over dx equals 0. X equals 1, dy over dx equals 0.2. X equals 2, dy over dx equals 0.4. X equals 3, dy over dx equals 0.6. X equals 4, dy over dx equals 0.8. X equals 5, dy over dx equals 1.0. Now try to put the pieces together, setting each so that the middle of its base is the proper distance to the right, and so that they fit together at the corners. Thus, figure 49. The result is, of course, not a smooth curve, but it is an approximation to one. If we had taken bits half as long and twice as numerous, like figure 50, we should have a better approximation. But for a perfect curve, we ought to take each dx and its corresponding dy infinitesimally small and infinitely numerous. Then how much ought the value of any y to be? Clearly, at any point P of the curve, the value of y will be the sum of all the little dy's from 0 up to that level. That is to say, integral dy equals y. And as each dy is equal to 1/5 x times dx, it follows that the whole y will be equal to the sum of all such bits as 1/5 x times dx, or as we should write it, integral 1/5 x times dx. Now if x had been constant, integral 1/5 x times dx would have been the same as 1/5 x integral dx, or 1/5 x squared. But x began by being 0, and increases to the particular value of x at the point P, so that its average value from 0 to that point is 1/2 x. Hence, integral 1/5 x dx equals 1/10 x squared, or y equals 1/10 x squared. But, as in the previous case, this requires the addition of an undetermined constant C, because we have not been told at what height above the origin the curve will begin when x equals 0. So we write, as the equation of the curve drawn in Figure 51, y equals 1/10 x squared plus C. End of section 40. Section 41 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Section 41. Exercises 16. 1. Find the ultimate sum of 2/3 plus 1/3 plus 1/6 plus 1/12 plus 1/24 plus etc. Answer: 1 1/3. 3. If log to the base epsilon of the quantity 1 plus x equals x minus the quantity x squared over 2 plus the quantity x cubed over 3 minus the quantity x to the 4th over 4 plus etc., find log to the base epsilon of 1.3. Answer: 0.2624. 4. Following a reasoning similar to that explained in this chapter, find y. A. If dy over dx equals 1/4 x. B. If dy over dx equals cosine x. Answers: A. Y equals 1/8 x squared plus C. B. Y equals sine x plus C. 5. If dy over dx equals 2x plus 3, find y. Answer: y equals x squared plus 3x plus C. End of section 41. Section 42 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating. Part 1. Differentiating is the process by which when y is given us as a function of x, we can find dy over dx. Like every other mathematical operation, the process of differentiation may be reversed. Thus, if differentiating y equals x to the 4th gives us dy over dx equals 4x cubed, if one begins with dy over dx equals 4x cubed, one would say that reversing the process would yield y equals x to the 4th. But here comes in a curious point. We should get dy over dx equals 4x cubed if we had begun with any of the following: x to the fourth, or x to the fourth plus a, or x to the fourth plus c, or x to the fourth with any added constant. So it is clear that in working backwards from dy over dx to y, one must make provision for the possibility of there being an added constant, the value of which will be undetermined until ascertained in some other way. So, if differentiating x to the n power yields nx to the n minus 1 power, going backwards from dy over dx equals nx to the n minus 1 power, will give us y equals x to the n power plus uppercase C, where uppercase C stands for the yet undetermined possible constant. Clearly, in dealing with powers of x, the rule for working backwards will be increase the power by 1, then divide by that increased power and add the undetermined constant. So, in the case where dy over dx equals x to the n power, working backwards, we get y equals the quantity 1 over n plus 1, n quantity, times x to the n plus 1 power, plus uppercase C. If differentiating the equation, y equals ax to the n power gives us dy over dx equals anx to the n minus 1 power, it is a matter of common sense that beginning with dy over dx equals anx to the n minus 1 power and reversing the process will give us y equals ax to the n power. So when we are dealing with a multiplying constant, we must simply put the constant as a multiplier of the result of the integration. Thus, if dy over dx equals 4x squared, the reverse process gives us y equals 4/3 x cubed. But this is incomplete, for we must remember that if we had started with y equals ax to the n power plus uppercase C, where uppercase C is any constant quantity whatever, we should equally have found dy over dx equals anx to the n minus 1 power. So therefore, when we reverse the process, we must always remember to add on this undetermined constant, even if we do not yet know what its value will be. This process, the reverse of differentiating, is called integrating, for it consists in finding the value of the whole quantity y when you are given only an expression for dy, or for dy over dx. Hitherto, we have as much as possible kept dy and dx together as a differential coefficient. Henceforth, we shall more often have to separate them. If we begin with a simple case, dy over dx equals x squared, we may write this, if we like, as dy equals x squared dx. Now this is a differential equation, which informs us that an element of y is equal to the corresponding element of x multiplied by x squared. Now what we want is the integral. Therefore, write down with the proper symbol the instructions to integrate both sides. Thus, integral dy equals integral x squared dx. We haven't yet integrated, we have only written down instructions to integrate. If we can, let us try. Plenty of other fools can do it, why not we also? The left-hand side is simplicity itself. The sum of all the bits of y is the same thing as y itself. So we may at once put y equals integral x squared dx. But when we come to the right-hand side of the equation, we must remember that what we have got to sum up together is not all the dx's, but all such terms as x squared dx. And this will not be the same as x squared integral dx, because x squared is not a constant. For some of the dx's will be multiplied by big values of x squared, and some will be multiplied by small values of x squared, according to what x happens to be. So we must bethink ourselves as to what we know about this process of integration being the reverse of differentiation. Now, our rule for this reversed process, when dealing with x to the nth power, is increase the power by 1 and divide by the same number as this increased power. That is to say, x squared dx will be changed to 1/3 x cubed. Footnote: you may ask, what has become of the little dx at the end? Well, remember that it was really part of the differential coefficient, and when changed over to the right-hand side, as in the x squared dx, serves as a reminder that x is the independent variable with respect to which the operation is to be effected, and, as a result of the product being totaled up, the power of x has increased by 1. You will soon become familiar with all this. End of footnote. Put this into the equation, but don't forget to add the constant of integration, uppercase C, at the end. So we get y equals 1/3 x cubed plus uppercase C. You have actually performed the integration. How easy! Let us try another simple case. Let dy over dx equal ax to the 12th, where a is any constant multiplier. Well, we found when differentiating that any constant factor in the value of y reappeared unchanged in the value of dy over dx. In the reversed process of integrating, it will therefore also reappear in the value of y. So we may go to work as before. Thus, dy equals ax to the 12th times dx. Integral dy equals integral ax to the 12th times dx. Integral dy equals a integral x to the 12th dx. Y equals a times 1/13 x to the 13th plus uppercase C. So that is done. How easy! We begin to realize now that integrating is a process of finding our way back, as compared with differentiating. If ever, during differentiating, we have found any particular expression, in this example, ax to the 12th, we can find our way back to the y from which it was derived. The contrast between the two processes may be illustrated by the following remark due to a well-known teacher. If a stranger were set down in Trafalgar Square and told to find his way to Euston Station, he might find the task hopeless. But if he had previously been personally conducted from Euston Station to Trafalgar Square, it would be comparatively easy to him to find his way back to Euston Station. End of section 42. Section 43 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating, Part 2. Integration of the sum or difference of two functions. Let dy over dx equal x squared plus x cubed. Then dy equals x squared dx plus x cubed dx. There is no reason why we should not integrate each term separately, for we found that when we differentiated the sum of two separate functions, the differential coefficient was simply the sum of the two separate differentiations. So when we work backwards, integrating, the integration will be simply the sum of the two separate integrations. Our instructions will then be integral dy equals integral of the quantity x squared plus x cubed dx equals integral x squared dx plus integral x cubed dx. Y equals 1/3 x cubed plus 1/4 x to the 4th plus uppercase C. If either of the terms had been a negative quantity, the corresponding term in the integral would have also been negative, so that differences are as readily dealt with as sums. End of section 43. Section 44 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as a reverse of differentiating. Part 3. How to deal with constant terms. Suppose there is, in the expression to be integrated, a constant term, such as this. dy over dx equals x to the nth plus b. This is laughably easy, for you have only to remember that when you differentiated the expression y equals ax, the result was dy over dx equals a. Hence, when you work the other way and integrate, the constant reappears, multiplied by x. So we get dy equals x to the nth dx plus b times dx. Integral dy equals integral x to the nth dx plus integral b dx. Y equals 1 over n plus 1, all times x to the n plus 1 power, plus bx plus uppercase C. Here are a lot of examples on which to try your newly acquired powers. Examples. 1. Given dy over dx equals 24 x to the 11th, find y. Answer. Y equals 2x to the 12th plus uppercase C. 2. Find the integral of the quantity a plus b times the quantity x plus 1 dx. It is the quantity a plus b integral the quantity x plus 1 dx. Or, open parenthesis, a plus b, close parenthesis, open bracket, integral x dx plus integral dx, close bracket. Or, open parenthesis, a plus b, close parenthesis, open parenthesis, the quantity x squared over 2, end quantity, plus x, close parenthesis, plus uppercase C. 3. Given du over dt equals gt to the 1/2 power, find u. Answer. U equals 2/3 gt to the 3 over 2 power, plus uppercase C. 4. dy over dx equals x cubed minus x squared plus x. Find y. dy equals, open parenthesis, x cubed minus x squared plus x, close parenthesis, dx. Or, dy equals x cubed dx minus x squared dx plus x dx. Y equals integral x cubed dx minus integral x squared dx plus integral x dx. And y equals 1/4 x to the 4th minus 1/3 x cubed plus 1/2 x squared plus uppercase C. 5. Integrate 9.75x to the 2.25 power dx. Answer. Y equals 3x to the 3.25 power plus uppercase C. All these are easy enough. Let us try another case. Let dy over dx equal ax to the minus 1 power. Proceeding as before, we will write dy equals ax to the minus 1 power times dx. Integral dy equals a integral x to the minus 1 power dx. Well, but what is the integral of x to the minus 1 power dx? If you look back amongst the results of differentiating x squared and x cubed and x to the nth, etc., you will find we never got x to the minus 1 power from any one of them as the value of dy over dx. We got 3x squared from x cubed, we got 2x from x squared, we got 1 from x to the 1 power, that is, from x itself. But we did not get x to the minus 1 power from x to the 0 power for two very good reasons. First, x to the 0 power is simply equal to 1, and is a constant, and could not have a differential coefficient. Secondly, even if it could be differentiated, its differential coefficient, got by slavishly following the usual rule, would be 0 times x to the minus 1 power, and that multiplication by 0 gives it 0 value. Therefore, when we now come to try to integrate x to the minus 1 power dx, we see that it does not come in anywhere in the powers of x that are given by the rule. Integral x to the nth dx equals the quantity 1 over n plus 1, end quantity, times x to the n plus 1 power. It is an exceptional case. Well, but try again. Look through all the various differentials obtained from various functions of x, and try to find amongst them x to the minus 1 power. A sufficient search will show that we actually did get dy over dx equals x to the minus 1 power as a result of differentiating the function y equals log base epsilon of x. Then, of course, since we know that differentiating log base epsilon of x gives us x to the minus 1 power, we know that by reversing the process, integrating dy equals x to the minus 1 power dx will give us y equals log base epsilon of x. But we must not forget the constant factor a that was given, nor must we omit to add the undetermined constant of integration. This then gives us as a solution to the present problem y equals a log base epsilon of x plus uppercase C. NB. Here note this very remarkable fact, that we could not have integrated in the above case if we had not happened to know the corresponding differentiation. If no one had found out that differentiating log base epsilon of x gave x to the minus 1 power, we should have been utterly stuck by the problem how to integrate x to the minus 1 power dx. Indeed, it should be frankly admitted that this is one of the curious features of the integral calculus, that you can't integrate anything before the reverse process of differentiating something else has yielded that expression which you want to integrate. No one, even today, is able to find the general integral of the expression dy over dx equals a to the minus x squared power, because a to the minus x squared power has never yet been found to result from differentiating anything else. Another simple case. Find integral of the quantity x plus 1 times quantity x plus 2 dx. On looking at the function to be integrated, you remark that it is the product of two different functions of x. You could, you think, integrate the quantity x plus 1 dx by itself, or the quantity x plus 2 dx by itself. Of course you could, but what to do with a product? None of the differentiations you have learned have yielded you for the differential coefficient a product like this. Failing such, the simplest thing is to multiply up the two functions and then integrate. This gives us integral of the quantity x squared plus 3x plus 2 dx. And this is the same as integral x squared dx plus integral 3x dx plus integral 2 dx. And performing the integrations, we get 1/3 x cubed plus 3 over 2 x squared plus 2x plus uppercase C. End of section 44. Section 45 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating. Part 4. Some other integrals. Now that we know that integration is the reverse of differentiation, we may at once look up the differential coefficients we already know and see from what functions they were derived. This gives us the following integrals ready-made. X to the minus 1 power. Integral x to the minus 1 power dx equals log base epsilon of x plus uppercase C. 1 over the quantity x plus a. Integral 1 over the quantity x plus a and quantity dx equals log base epsilon of the quantity x plus a and quantity plus uppercase C. Epsilon to the x power. Integral epsilon to the x power dx equals epsilon to the x power plus uppercase C. Epsilon to the minus x power. Integral epsilon to the minus x power dx equals minus epsilon to the minus x power plus uppercase C. For if y equals minus 1 over epsilon to the x power, dy over dx equals minus numerator epsilon to the x power times 0 minus 1 times epsilon to the x power, and numerator all over denominator epsilon to the 2x power, and denominator equals epsilon to the minus x power. Sine x, integral sine x dx equals minus cosine x plus uppercase C. Cosine x, integral cosine x dx equals sine x plus uppercase C. Also, we may deduce the following. Log base epsilon of x, integral log base epsilon of x dx equals x of the quantity log base epsilon of x minus 1, and quantity plus uppercase C. For if y equals x log base epsilon of x minus x, dy over dx equals x over x plus log base epsilon of x minus 1 equals log base epsilon of x. Log base 10 of x. Integral log base 10 of x dx equals 0.4343x of the quantity log base epsilon of x minus 1, and quantity plus uppercase C. A to the x power. Integral a to the x power dx equals the quantity a to the x power over log base epsilon of a, and quantity plus uppercase C. Cosine ax. Integral cosine ax dx equals the quantity 1 over a and quantity sine ax plus uppercase C. For if y equals sine ax, dy over dx equals a cosine ax. Hence, to get cosine ax, one must differentiate y equals the quantity 1 over a and quantity sine ax. Sine ax, integral sine ax dx equals minus the quantity 1 over a and quantity cosine ax plus uppercase C. Try also cosine squared theta. A little dodge will simplify matters. Cosine 2 theta equals cosine squared theta minus sine squared theta equals 2 cosine squared theta minus 1. Hence, cosine squared theta equals 1/2 times the quantity cosine 2 theta plus 1, and integral cosine squared theta d theta equals 1/2 integral the quantity cosine 2 theta plus 1 and quantity d theta equals 1/2 integral cosine 2 theta d theta plus 1/2 integral d theta equals the quantity sine 2 theta over 4 and quantity plus the quantity theta over 2 and quantity plus uppercase C. See also the table of standard forms on pages 249 to 251. You should make such a table for yourself, putting in it only the general functions which you have successfully differentiated and integrated. See to it that it grows steadily. End of section 45. Section 46 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating. Part 5. On double and triple integrals. In many cases, it is necessary to integrate some expression for two or more variables contained in it, and in that case, the sign of integration appears more than once. Thus, integral of function f of x, y, end function dx dy means that some function of the variables x and y has to be integrated for each. It does not matter in which order they are done. Thus, take the function x squared plus y squared. Integrating it with respect to x gives us integral x squared plus y squared dx equals 1/3 x cubed plus xy squared. Now integrate this with respect to y. Integral 1/3 x cubed plus xy squared dy equals 1/3 x cubed y plus 1/3 xy cubed, to which of course a constant is to be added. If we had reversed the order of the operations, the result would have been the same. In dealing with areas of surfaces and of solids, we have often to integrate both for length and breadth, and thus have integrals of the form integral u times dx dy, where u is some property that depends, at each point, on x and on y. This would then be called a surface integral. It indicates that the value of all such elements as u times dx times dy, that is to say, of the value of u over a little rectangle dx long and dy broad, has to be summed up over the whole length and whole breadth. Similarly, in the case of solids, where we deal with 3 dimensions. Consider any element of volume, the small cube whose dimensions are dx, dy, dz. If the figure of the solid be expressed by the function f of x, y, z, then the whole solid will have the volume integral. Volume equals integral of function f of x, y, z, end function, times dx times dy times dz. Naturally, such integrations have to be taken between appropriate limits in each dimension, and the integration cannot be performed unless one knows in what way the boundaries of the surface depend on x, y, and z. If the limits for x are from x sub 1 to x sub 2, those for y from y sub 1 to y sub 2, and those for z from z sub 1 to z sub 2, then clearly we have volume equals integral from z sub 1 to z sub 2, integral from y sub 1 to y sub 2, integral from x sub 1 to x sub 2 of function f of x, y, z, end function, times dx times dy times dz. There are, of course, plenty of complicated and difficult cases, but in general it is quite easy to see the significance of the symbols where they are intended to indicate that a certain integration has to be performed over a given surface, or throughout a given solid space. End of section 46. Section 47 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Section 47. Exercises 17. 1. Find integral y dx when y squared equals 4ax. Answer: numerator 4 times the square root of a times x to the 3 over 2 power, and numerator, all over denominator 3, and denominator plus uppercase C. 2. Find integral 3 over x to the 4th power dx. Answer, minus the quantity 1 over x cubed and quantity plus uppercase C. 3. Find integral the quantity 1 over a and quantity x cubed dx. Answer, the quantity x to the 4th power over 4a and quantity plus uppercase C. 4. Find integral of the quantity x squared plus a and quantity dx. Answer, 1/3 x cubed plus ax plus uppercase C. 5. Integrate 5x to the minus 7 over 2 power. Answer, minus 2x to the minus 5 over 2 power plus uppercase C. 6. Find integral of the quantity 4x cubed plus 3x squared plus 2x plus 1 and quantity dx. Answer, x to the 4th power plus x cubed plus x squared plus x plus uppercase C. 7. If dy over dx equals the quantity ax over 2 plus the quantity bx squared over 3 plus the quantity cx cubed over 4, find y. Answer, the quantity ax squared over 4 plus the quantity bx cubed over 9 plus the quantity cx to the 4th power over 16 plus uppercase C. 8. Find integral of the quantity x squared plus a all over x plus a and quantity dx. Answer, x squared plus a all over x plus a equals x minus a plus the quantity a squared plus a all over x plus a and quantity by division. Therefore, the answer is the quantity x squared over 2 and quantity minus ax plus the quantity a squared plus a and quantity log base epsilon of the quantity x plus a and quantity plus uppercase C. 9. Find integral of the quantity x plus 3 and quantity cubed dx. Answer, the quantity x to the 4th power over 4 and quantity plus 3x cubed plus the quantity 27 over 2 and quantity x squared plus 27x plus uppercase C. 10. Find integral of the quantity x plus 2 times the quantity x minus a dx. Answer, the quantity x cubed over 3 plus the quantity 2 minus a over 2 and quantity times x squared minus 2ax plus uppercase C. 11. Find integral of the quantity the square root of x plus the cube root of x and quantity times 3a squared dx. Answer, a squared times the quantity 2x to the 3 over 2 power plus 9 over 4x to the 4 over 3 power and quantity plus uppercase C. 12. Find integral of the quantity sine theta minus 1/2 and quantity d theta over 3. Answer, minus 1/3 cosine theta minus 1/6 theta plus uppercase C. 13. Find integral cosine squared a theta d theta. Answer, theta over 2 plus the quantity sine 2a theta over 4a and quantity plus uppercase C. 14. Find integral sine squared theta d theta. Answer, theta over 2 minus the quantity sine 2 theta over 4 and quantity plus uppercase C. 15. Find integral sine squared a theta d theta. Answer, theta over 2 minus the quantity sine 2a theta over 4a, end quantity, plus uppercase C. 16. Find integral epsilon to the 3x power dx. Answer: 1/3 epsilon to the 3x power, plus uppercase C. 17. Find integral dx over 1 plus x. Answer: log base epsilon of the quantity 1 plus x, end quantity, plus uppercase C. 18. Find integral dx over 1 minus x. Answer: minus log base epsilon of the quantity 1 minus x, end quantity, plus uppercase C. End of section 47. Section 48 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19. On Finding Areas by Integrating, Part 1. One use of the integral calculus is to enable us to ascertain the values of areas bounded by curves. Let us try to get at the subject bit by bit. Let uppercase AB, figure 52, be a curve, the equation to which is known. That is, y in this curve is some known function of x. Think of a piece of the curve from the point uppercase P to the point uppercase Q. Let a perpendicular uppercase PM be dropped from uppercase P, and another uppercase QN from the point uppercase Q. Then call uppercase OM equals x sub 1 and uppercase ON equals x sub 2, and the ordinates uppercase PM equals y sub 1 and uppercase QN equals y sub 2. We have thus marked out the area uppercase PQNM that lies beneath the piece uppercase PQ. The problem is, how can we calculate the value of this area? The secret of solving this problem is to conceive the area as being divided up into a lot of narrow strips, each of them being of the width dx. The smaller we take dx, the more of them there will be between x sub 1 and x sub 2. Now the whole area is clearly equal to the sum of the areas of all such strips. Our business will then be to discover an expression for the area of any one narrow strip, and to integrate it so as to add together all the strips. Now think of any one of the strips. It will be like this, being bounded between two vertical sides, with a flat bottom dx, and with a slightly curved, sloping top. Suppose we take its average height as being y. Then, as its width is dx, its area will be y dx. And seeing that we may take the width as narrow as we please, if we only take it narrow enough, its average height will be the same as the height at the middle of it. Now let us call the unknown value of the whole area uppercase S, meaning surface. The area of one strip will be simply a bit of the whole area, and may therefore be called d uppercase S. So we may write area of one strip equals d uppercase S equals y times dx. If then we add up all the strips, we get total area uppercase S equals integral d uppercase S equals integral y dx. So then our finding uppercase S depends on whether we can integrate y times dx for the particular case, when we know what the value of y is as a function of x. For instance, if you were told that for the particular curve in question, y equals b plus ax squared, no doubt you could put that value into the expression and say, then I must find integral of the quantity b plus ax squared and quantity dx. That is all very well, but a little thought will show you that something more must be done. because the area we are trying to find is not the area under the whole length of the curve, but only the area limited on the left by uppercase PM and on the right by uppercase QN, it follows that we must do something to define our area between those limits. This introduces us to a new notion, namely that of integrating between limits. We suppose x to vary, and for the present purpose we do not require any value of x below x sub 1, that is, uppercase OM, nor any value of x above x sub 2, that is, uppercase ON. When an integral is to be thus defined between two limits, we call the lower of the two values the inferior limit, and the upper value the superior limit. Any integral so limited we designate as a definite integral, by way of distinguishing it from a general integral, to which no limits are assigned. In the symbols which give instructions to integrate, the limits are marked by putting them at the top and bottom, respectively, of the sign of integration. Thus, the instruction, integral from x equals x sub 1 to x equals x sub 2 of y times dx, will be read, find the integral of y times dx between the inferior limit, x sub 1, and the superior limit, x sub 2. Sometimes the thing is written more simply, integral from x sub 1 to x sub 2 of y times dx. Well, but how do you find an integral between limits when you have got these instructions? Look again at figure 52. Suppose we could find the area under the larger piece of curve from uppercase A to uppercase Q, that is from x equals 0 to x equals x sub 2, naming the area uppercase AQNO. Then suppose we could find the area under the smaller piece from uppercase A to uppercase P, that is from x equals 0 to x equals x sub 1, namely the area uppercase APMO. If then we were to subtract the smaller area from the larger, we should have left as a remainder the area uppercase PQNM, which is what we want. Here we have the clue as to what to do. The definite integral between the two limits is the difference between the integral worked out for the superior limit and the integral worked out for the lower limit. Let us then go ahead. First, find the general integral thus, integral y dx. And, as y equals b plus ax squared is the equation to the curve in figure 52, integral of the quantity b plus ax squared and quantity dx is the general integral which we must find. Doing the integration in question by the rule, we get bx plus the quantity a over 3 and quantity times x cubed plus uppercase C. And this will be the whole area from 0 up to any value of x that we may assign. Therefore, the larger area up to the superior limit x sub 2 will be bx sub 2 plus the quantity a over 3 and quantity times x sub 2 cubed plus uppercase C. And the smaller area up to the inferior limit x sub 1 will be bx sub 1 plus the quantity a over 3 and quantity times x sub 1 cubed plus uppercase C. Now subtract the smaller from the larger, and we get for the area uppercase S the value area uppercase S equals b times the quantity x sub 2 minus x sub 1 and quantity plus a over 3 times the quantity x sub 2 cubed minus x sub 1 cubed. This is the answer we wanted. Let us give some numerical values. Suppose b equals 10, a equals 0.06, and x sub 2 equals 8, and x sub 1 equals 6. Then the area uppercase S is equal to 10 times the quantity 8 minus 6 plus 0.06 over 3 times the quantity 8 cubed minus 6 cubed equals 20 plus 0.02 times the quantity 512 minus 216 equals 20 plus 0.02 times 296 equals 20 plus 5.92 equals 25.92. Let us here put down a symbolic way of stating what we have ascertained about limits. Integral from x equals x sub 1 to x equals x sub 2 of y dx equals y sub 2 minus y sub 1, where y sub 2 is the integrated value of y dx, corresponding to x sub 2, and y sub 1 that corresponding to x sub 1. All integration between limits requires the difference between two values to be thus found. Also note that, in making the subtraction, the added constant uppercase C has disappeared. Examples. 1. To familiarize ourselves with the process, let us take a case of which we know the answer beforehand. Let us find the area of the triangle which has base x equals 12 and height y equals 4. We know beforehand, from obvious mensuration, that the answer will come 24. Now here we have as the curve a sloping line for which the equation is y equals x over 3. The area in question will be integral from x equals 0 to x equals 12 of y times dx equals integral from x equals 0 to x equals 12 of x over 3 times dx. Integrating x over 3 times dx and putting down the value of the general integral in square brackets with the limits marked above and below, we get area equals, open bracket, 1/3 times 1/2 x squared, close bracket, from x equals 0 to x equals 12, plus uppercase C, equals, open bracket, x squared over 6, close bracket, from x equals 0 to x equals 12, plus uppercase C, equals, open bracket, 12 squared over 6, close bracket, minus, open bracket, 0 squared over 6, close bracket, equals 144 over 6, equals 24, which is the answer. Let us satisfy ourselves about this rather surprising dodge of calculation by testing it on a simple example. Get some squared paper, preferably some that is ruled in little squares of 1/8 inch or 1/10 inch each way. On this squared paper, plot out the graph of the equation y equals x over 3. The values to be plotted will be x equals 0, y equals 0, x equals 3, y equals 1, x equals 6, y equals 2, x equals 9, y equals 3, x equals 12, y equals 4. Now reckon out the area beneath the curve by counting the little squares below the line, from x equals 0 as far as x equals 12 on the right. There are 18 whole squares and 4 triangles, each of which has an area equal to 1 1/2 squares, or in total 24 squares. Hence 24 is the numerical value of the integral of x over 3 dx between the lower limit of x equals 0 and the higher limit of x equals 12. As a further exercise, show that the value of the same integral between the limits of x equals 3 and x equals 15 is 36. 2. Find the area between limits x equals x sub 1 and x equals 0 of the curve y equals b over x plus a. Area equals integral from x equals 0 to x equals x sub 1 of y times dx equals integral from x equals 0 to x equals x sub 1 of b over x plus a dx equals b, open bracket, log base epsilon of the quantity x plus a, close bracket, from 0 to x sub 1, plus uppercase C, equals b, open bracket, log base epsilon of the quantity x sub 1 plus a, minus log base epsilon of the quantity 0 plus a, close bracket, equals b log base epsilon of the quantity numerator x sub 1 plus a over denominator a, which is the answer. NB. Notice that in dealing with definite integrals, the constant uppercase C always disappears by subtraction. Let it be noted that this process of subtracting one part from a larger to find the difference is really a common practice. How do you find the area of a plane ring, the outer radius of which is r sub 2 and the inner radius is r sub 1? You know from mensuration that the area of the outer circle is pi r sub 2 squared. Then you find the area of the inner circle, pi r sub 1 squared. Then you subtract the latter from the former and find area of ring equals pi times the quantity r sub 2 squared minus r sub 1 squared, which may be written pi times the quantity r sub 2 plus r sub 1 times the quantity r sub 2 minus r sub 1 equals mean circumference of ring times width of ring. 3. Here's another case, that of the die-away curve. Find the area between x equals 0 and x equals a of the curve whose equation is y equals b epsilon to the minus x power. Area equals b integral from x equals 0 to x equals a of epsilon to the minus x power times dx. The integration gives equals b open bracket minus epsilon to the minus x power close bracket from 0 to a equals b open bracket the quantity minus epsilon to the minus a power minus the quantity minus epsilon to the minus 0 power close bracket equals b times the quantity 1 minus epsilon to the minus a power. 4. Another example is afforded by the adiabatic curve of a perfect gas, the equation to which is PV to the n power equals C, where P stands for pressure, V for volume, and n is of the value 1.42. Find the area under the curve, which is proportional to the work done in suddenly compressing the gas from volume V sub 2 to volume V sub 1. Here we have area equals integral from V equals V sub 1 to V equals V sub 2 of CV to the minus n power times dV equals C, open bracket, the quantity 1 over 1 minus n quantity, times V to the 1 minus n power, close bracket, from V sub 1 to V sub 2 equals C times the quantity 1 over 1 minus n, end quantity, times the quantity V sub 2 to the 1 minus n power minus V sub 1 to the 1 minus n power, equals the quantity minus C over 0.42, end quantity, times the quantity 1 over V sub 2 to the 0.42 power minus 1 over V sub 1 to the 0.42 power. An exercise. Prove the ordinary mensuration formula that the area uppercase A of a circle whose radius is uppercase R is equal to pi uppercase R squared. Consider an elementary zone or annulus of the surface of breadth dr situated at a distance r from the center. We may consider the entire surface as consisting of such narrow zones, and the whole area uppercase A will simply be the integral of all such elementary zones from center to margin, that is, integrated from r equals 0 to r equals uppercase R. We have therefore to find an expression for the elementary area d uppercase A of the narrow zone. Think of it as a strip of breadth dr and of a length that is the periphery of the circle of radius r, that is, a length of 2 pi r. Then we have as the area of the narrow zone d uppercase A equals 2 pi r dr. Hence, the area of the whole circle will be uppercase A equals integral d uppercase A equals integral from r equals 0 to r equals uppercase R of 2 pi r times dr equals 2 pi integral from r equals 0 to r equals uppercase R of r times dr. Now the general integral of r times dr is 1/2 r squared. Therefore, uppercase A equals 2 pi, open bracket, 1/2 r squared, close bracket, from r equals 0 to r equals uppercase R. Or, uppercase A equals 2 pi, open bracket, 1/2 uppercase R squared minus 1/2 times 0 squared, close bracket. Whence, uppercase A equals pi uppercase R squared. Another exercise. Let us find the mean ordinate of the positive part of the curve y equals x minus x squared. To find the mean ordinate, we shall have to find the area of the piece, uppercase OMN, and then divide it by the length of the base, uppercase ON. But before we can find the area, we must ascertain the length of the base, so as to know up to what limit we are to integrate. At uppercase N, the ordinate y has 0 value. Therefore, we must look at the equation and see what value of x will make y equal 0. Now clearly, if x is 0, y will also be 0, the curve passing through the origin, uppercase O. But also, if x equals 1, y equals 0, so that x equals 1 gives us the position of the point uppercase N. Then the area wanted is equals integral from x equals 0 to x equals 1 of the quantity x minus x squared dx equals, open bracket, 1/2 x squared minus 1/3 x cubed, close bracket, from 0 to 1 equals, open bracket, 1/2 minus 1/3, close bracket, minus, open bracket, 0 minus 0, close bracket, equals 1/6. But the base length is 1. Therefore, the average ordinate of the curve equals 1/6. NB. It will be a pretty and simple exercise in maxima and minima to find by differentiation what is the height of the maximum ordinate. It must be greater than the average. The mean ordinate of any curve over a range from x equals 0 to x equals x sub 1 is given by the expression mean y equals 1 over x sub 1 integral from x equals 0 to x equals x sub 1 of y times dx. One can also find in the same way the surface area of a solid of revolution. Example. The curve y equals x squared minus 5 is revolving about the axis of x. Find the area of the surface generated by the curve between x equals 0 and x equals 6. A point on the curve, the ordinate of which is y, describes a circumference of length 2 pi y, and a narrow belt of the surface of width dx corresponding to this point has for area 2 pi y dx. The total area is 2 pi integral from x equals 0 to x equals 6 of y dx equals 2 pi integral from x equals 0 to x equals 6 of the quantity x squared minus 5 dx equals 2 pi, open bracket, x cubed over 3 minus 5x, close bracket, from 0 to 6 equals 6.28 times 42 equals 263.76. End of section 48. Section 49 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19. On Finding Areas by Integrating. Part 2. Areas in Polar Coordinates. When the equation of the boundary of an area is given as a function of the distance r of a point of it from a fixed point O, called the pole, and of the angle which r makes with the positive horizontal direction OX, the process just explained can be applied just as easily, with a small modification. Instead of a strip of area, we consider a small triangle OAB, the angle at O being d theta, and we find the sum of all the little triangles making up the required area. The area of such a small triangle is approximately the quantity A_B over 2 n quantity times r, or the quantity r d theta over 2 n quantity times r. Hence the portion of the area included between the curve and two positions of r, corresponding to the angles theta sub 1 and theta sub 2, is given by 1/2 integral from theta equals theta sub 1 to theta equals theta sub 2 of r squared d theta. Examples. 1. Find the area of the sector of 1 radian in a circumference of radius a inches. The polar equation of the circumference is evidently r equals a. The area is 1/2 integral from theta equals theta sub 1 to theta equals theta sub 2 of a squared d theta equals a squared over 2 integral from theta equals 0 to theta equals 1 of d theta equals a squared over 2. 2. Find the area of the first quadrant of the curve, known as Pascal's snail, the polar equation of which is r equals a times the quantity 1 plus cosine theta. Area equals 1/2 integral from theta equals 0 to theta equals pi over 2 of a squared times the quantity 1 plus cosine theta end quantity squared d theta equals a squared over 2 integral from theta equals 0 to theta equals pi over 2 of the quantity 1 plus 2 cosine theta plus cosine squared theta end quantity d theta equals a squared over 2 open bracket theta plus 2 sine theta plus theta over 2 plus sine 2 theta over 4 close bracket from 0 to pi over 2 equals numerator a squared times the quantity 3 pi plus 8 and numerator over denominator 8. End of section 49. Section 50 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19. On Finding Areas by Integrating. Part 3. Volumes by Integration. What we have done with the area of a little strip of a surface, we can, of course, just as easily do with the volume of a little strip of a solid. We can add up all the little strips that make up the total solid and find its volume, just as we have added up all the small little bits that made up an area to find the final area of the figure operated upon. Examples. 1. Find the volume of a sphere of radius r. A thin spherical shell has for volume 4 pi x squared dx. Summing up all the concentric shells which make up the sphere, we have volume sphere equals integral from x equals 0 to x equals r of 4 pi x squared dx equals 4 pi open bracket x cubed over 3 close bracket from 0 to r equals 4 over 3 pi r cubed. We can also proceed as follows. A slice of the sphere of thickness dx has for volume pi y squared dx. Also, x and y are related by the expression y squared equals r squared minus x squared. Hence, volume sphere equals 2 integral from x equals 0 to x equals r of pi times the quantity r squared minus x squared and quantity dx equals 2 pi open bracket integral from x equals 0 to x equals r of r squared dx minus integral from x equals 0 to x equals r of x squared dx close bracket equals 2 pi open bracket r squared x minus the quantity x cubed over 3 close bracket from 0 to r equals the quantity 4 pi over 3 and quantity r cubed. 2. Find the volume of the solid generated by the revolution of the curve y squared equals 6x about the axis of x between x equals 0 and x equals 4. The volume of a strip of the solid is pi y squared dx. Hence, volume equals integral from x equals 0 to x equals 4 of pi y squared dx equals 6 pi integral from x equals 0 to x equals 4 of x dx equals 6 pi open bracket x squared over 2 close bracket from 0 to 4 equals 48 pi equals 150.8. End of section 50. Section 51 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19. On Finding Areas by Integrating. Part 4. On Quadratic Means. In certain branches of physics, particularly in the study of alternating electric currents, it is necessary to be able to calculate the quadratic mean of a variable quantity. By quadratic mean is denoted the square root of the mean of the squares of all the values between the limits considered. Other names for the quadratic mean of any quantity are its virtual value or its RMS, meaning root mean square value. The French term is valeur efficace. If y is the function under consideration, and the quadratic mean is to be taken between the limits of x equals 0 and x equals L, then the quadratic mean is expressed as the square root of the quantity 1 over L integral from 0 to L of y squared dx. Examples. 1. To find the quadratic mean of the function y equals ax. Here the integral is integral from 0 to L of a squared x squared dx, which is 1/3 a squared L cubed. Dividing by L and taking the square root, we have quadratic mean equals the quantity 1 over the square root of 3 and quantity AL. Here the arithmetical mean is 1/2 AL, and the ratio of quadratic to arithmetical mean, this ratio is called the form factor, is 2 over the square root of 3 equals 1.155. 2. To find the quadratic mean of the function y equals x to the a power, the integral is integral from x equals 0 to x equals L of x to the 2a power dx. That is, numerator L to the 2a plus 1 power over denominator 2a plus 1. Hence, quadratic mean equals the square root of the quantity, numerator L to the 2a power over denominator 2a plus 1. 3. To find the quadratic mean of the function y equals a to the x over 2 power. The integral is integral from x equals 0 to x equals L of, open parenthesis, a to the x over 2 power, close parenthesis, squared dx. That is, integral from x equals 0 to x equals L of a to the x power dx. Or, open bracket, a to the x power over log base epsilon of a, close bracket, from x equals 0 to x equals L, which is, numerator, the quantity a to the L power in quantity minus 1 over denominator log base epsilon of a. Hence the quadratic mean is the square root of the quantity, numerator a to the L power minus 1 over denominator L log base epsilon of a. End of section 51.
Section 52 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 52. Exercises 18. 1. Find the area of a curve y equals x squared add x minus 5 between x equals 0 and x equals 6, and the mean ordinates between these limits. Answer. Area equals 60, mean ordinate equals 10. 2. Find the area of the parabola y equals 2a root x between x equals 0 and x equals a. Show that it is 2/3 of the rectangle of the limiting ordinate and of its abscissa. Answer. Area equals 2/3 of a times 2a root a. 3. Find the area of the positive portion of a sine curve and the mean ordinate. Answer. Area equals 2, mean ordinate equals 2 over pi equals 0.637. 4. Find the area of the positive portion of the curve y equals sin squared x and find the mean ordinate. Answer. Area equals 1.57, mean ordinate equals 0.5. 5. Find the area included between the two branches of the curve y equals x squared plus minus x to the power of 5 over 2, from x equals 0 to x equals 1. Also the area of the positive portion of the lower branch of the curve. Answer. 0.572, 0.0476. 6. Find the volume of a cone of radius of base r and of height h. Answer. Volume equals pi r squared h over 3. 7. Find the area of the curve y equals x cubed minus log base ex between x equals 0 and x equals 1. Answer. 1.25. 8. Find the volume generated by the curve y equals the square root of 1 add x squared, as it revolves around the axis of x between x equals 0 and x equals 4. Answer. 79.4. 9. Find the volume generated by a sine curve revolving around the axis of x. Find also the area of its surface. Answer. Volume equals 4.9348. Area of surface equals 12.57 from 0 to pi. 10. Find the area of the portion of the curve xy equals a included between x equals 1 and x equals a. Find the mean ordinate between these limits. Answer. A log base ea, a over a minus 1 log base ea. 11. Show that the quadratic mean of the function y equals sin x between the limits of 0 and pi radians is √2/2. Find also the arithmetical mean of the same function between the same limits, and show that the form factor is 1.11. 12. Find the arithmetical and quadratic means of the function x² add 3x add 2 from x equals 0 to x equals 3. Answer. Arithmetical mean 9.5. Quadratic mean 10.85. 13. Find the quadratic mean and the arithmetical mean of the function a1 sin x add a3 sin 3x. Answer. Quadratic mean equals 1/√2 times the square root of a1 squared add a3 squared. Arithmetical mean equals 0. The first involves a somewhat difficult integral, and may be stated thus. By definition, the quadratic mean will be the square root of 1/2 pi integral between 0 and 2 pi, open brackets, a1 sin x add a3 sin 3x, close brackets, squared dx. Now the integration indicated by integral open brackets a1 squared sin squared x add 2a1 a3 sin x sin 3x add a3 squared sin squared 3x, close brackets, dx, is more readily obtained if for sin squared x we write 1 minus cos 2x all over 2. For 2 sin x sin 3x we write cos 2x minus cos 4x, and for sin squared 3x 1 minus cos 6x all over 2. Making these substitutions and integrating, we get a1 squared over 2, open brackets, x minus sin 2x all over 2, close brackets, add a1, a3, open brackets, sin 2x all over 2 minus sin 4x all over 4, close brackets, add a3 squared over 2, open brackets, x minus sin 6x all over 6, close brackets. At the lower limit, the substitution of 0 for x causes all this to vanish, while at the upper limit the substitution of 2 pi for x gives a1 squared pi add a3 squared pi, and hence the answer follows. 14. A certain curve has the equation y equals 3.42 times e to the power of 0.21x. Find the area included between the curve and the axis of x from the ordinate at x equals 2 to the ordinate at x equals 8. Find also the height of the mean ordinate of the curve between these points. Answer. Area equals 62.6 square units. Mean ordinate is 10.42. 15. Show that the radius of a circle, the area of which is twice the area of a polar diagram, is equal to the quadratic mean of all the values of r for that polar diagram. 16. Find the volume generated by the curve y equals plus or minus x over 6 times the square root of x open brackets 10 minus x close brackets, rotating about the axis of x. Answer. 436.3. This solid is pear-shaped. End of section 52. Section 53 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 20. Dodges, Pitfalls and Triumphs. Dodges. A great part of the labour of integrating things consists in licking them into some shape that can be integrated. The books, and by this is meant the serious books, on the integral calculus are full of plans and methods and dodges and artifices for this kind of work. The following are a few of them. Integration by parts. This name is given to a dodge, the formula for which is integral u dx equals ux minus integral x du add c. It is useful in some cases that you can't tackle directly, for it shows that if in any case integral x du can be found, then integral u dx can also be found. The formula can be deduced as follows. From page 37 we have d open brackets ux close brackets equals u dx add x du, which may be written u dx equals open brackets d ux close brackets minus x du, which by direct integration gives the above expression. Examples. 1. Find integral w sin w dw. Write u equals w, and for sin w dw write dx. We shall then have du equals dw, while integral sin w dw equals minus cos w equals x. Putting these into the formula, we get integral w sin w dw equals w open brackets minus cos w close brackets minus integral minus cos w dw equals minus w cos w add sin w add c. 2. Find integral x e to the power of x dx. Write u equals x, e to the power of x dx equals dv, then du equals dx, v equals e to the power of x, and integral x e to the power of x dx equals x e to the power of x minus integral e to the power of x dx by the formula equals x e to the power of x minus e to the power of x equals e to the power of x open brackets x minus 1 close brackets add c. 3. Try integral cos squared theta d theta. U equals cos theta d theta equals dv. Hence, du equals minus sin theta d theta, v equals sin theta. Integral cos squared theta d theta equals cos theta sin theta add integral sin squared theta d theta equals 2 cos theta sin theta all over 2 add integral open brackets 1 minus cos squared theta close brackets d theta equals sin 2 theta all over 2 add integral d theta minus integral cos squared theta d theta. Hence 2 integral cos squared theta d theta equals sin 2 theta all over 2 add theta, and integral cos squared theta d theta equals 2 sin theta all over 4 add theta over 2 add c. 4. Find integral x squared sin x dx. Write x squared equals u, sin x dx equals dv. Then du equals 2x dx, v equals minus cos x. Integral x squared sin x dx equals minus x squared cos x add to integral x cos x dx. Now find integral x cos x dx integrating by parts, as in example 1 above. Integral x cos x dx equals x sin x add cos x add c. Hence, x squared sin x dx equals minus x squared cos x add 2x sin x add 2 cos x add c dash equals 2 open brackets x sin x add cos x open brackets 1 minus x squared over 2 close brackets add c dash. 5. Find integral square root of 1 minus x squared dx. Write u equals square root of 1 minus x squared dx equals dv. Then du equals minus x dx over square root of 1 minus x squared and x equals v, so that integral square root of 1 minus x squared dx equals x square root 1 minus x squared add integral x squared dx over square root of 1 minus x squared. Here we may use a little dodge, for we can write integral the square root of 1 minus x squared dx equals integral open brackets 1 minus x squared close brackets dx all over the square root of 1 minus x squared equals dx over the square root of 1 minus x squared minus integral x squared dx over the square root of 1 minus x squared. Adding these two last equations, we get rid of integral x squared dx over the square root of 1 minus x squared, and we have 2 integral square root of 1 minus x squared dx equals x times the square root of 1 minus x squared, add integral dx over the square root of 1 minus x squared. Do you remember meeting dx over the square root of 1 minus x squared? It is got by differentiating y equals arc sin x. Hence its integral is arc sin x, and so integral square root of 1 minus x squared dx equals x square root of 1 minus x squared all over 2, add a half arc sin x, add c. You can try now some exercises by yourself. You will find some at the end of this chapter. Substitution. This is the same dodge as explained in chapter 9, page 66. Let us illustrate its application to integration by a few examples. 1. Integral square root of 3 add x dx. Let 3 add x equals u, dx equals du. Replace integral u to the power of a half du equals 2 over 3 u to the power of 3 over 2 equals 2 over 3 open brackets 3 add x close brackets to the power of 3 over 2. 2. Integral dx over e to the power of x add e to the power of minus x. Let e to the power of x equals u, du over dx equals e to the power of x, and dx equals du over e to the power of x. So that dx over e to the power of x add e to the power of minus x equals integral du over e to the power of x open brackets e to the power of x add e to the power of minus x close brackets equals integral du over u open brackets u add 1 over u close brackets equals integral du over u squared add 1. Du over u squared add 1 is the result of differentiating arctan x. Hence the integral is arctan e to the power of x. 3. Integral dx over x squared add 2x add 3 equals integral dx over x squared add 2x add 1 add 2 equals integral dx over open brackets x add 1 close brackets squared add open brackets square root of 2 close brackets squared. Let x add 1 equals u, dx equals du. Then the integral becomes integral du over u squared add open brackets square root of 2 close brackets squared. But du over u squared add a squared is the result of differentiating u equals 1 over a arctan u over a. Hence one has finally 1 over the square root of 2 arctan x add 1 all over the square root of 2 for the value of the given integral. Formulae of reduction are special forms applicable chiefly to binomial and trigonometrical expressions that have to be integrated and have to be reduced into some form of which the integral is known. Rationalization and factorization of denominator are dodges applicable in special cases, but they do not admit any short or general explanation. Much practice is needed to become familiar with these preparatory processes. The following example shows how the process of splitting into partial fractions, which we learned in chapter 13, page 118, can be made use of in integration. Take again integral dx over x squared add 2x add 3. If we split 1 over x squared add 2x add 3 into partial fractions, this becomes 1 over 2 square root of minus 2, open brackets, integral dx over x add 1 minus square root of minus 2, minus integral dx over x add 1 add the square root of minus 2, close brackets, equals 1 over 2 square root of minus 2 log base e, x add 1 minus square root of minus 2 over x add 1 add square root of minus 2. Notice that the same integral can be expressed sometimes in more than one way, which are equivalent to one another. Pitfalls. A beginner is liable to overlook certain points that a practised hand would avoid, such as the use of factors that are equivalent to either 0 or infinity, and the occurrence of indeterminate quantities such as 0/0. There is no golden rule that will meet every possible case. Nothing but practice and intelligent care will avail. An example of a pitfall which had to be circumvented arose in Chapter XVIII, page 189, when we came to the problem of integrating x⁻⁻1 dx. Triumphs. By triumphs must be understood the successes with which the calculus has been applied to the solution of problems otherwise intractable. Often in the consideration of physical relations one is able to build up an expression for the law governing the interaction of the parts or the forces that govern them, such expression being naturally in the form of a differential equation, that is, an equation containing differential coefficients with or without other algebraic quantities. And when such a differential equation has been found, one can get no further until it has been integrated. Generally, it is much easier to state the appropriate differential equation than to solve it. The real trouble begins then only when one wants to integrate, unless indeed the equation is seen to possess some standard form of which the integral is known, and then the triumph is easy. The equation which results from integrating a differential equation is called its solution. And it is quite astonishing how in many cases the solution looks as if it had no relation to the differential equation of which it is the integrated form. Footnote. This means that the actual result of solving it is called its solution, but many mathematicians would say, with Professor Forsyth, every differential equation is considered as solved when the value of the dependent variable is expressed as a function of the independent variable by means either of known functions or of integrals, whether the integration in the latter can or cannot be expressed in terms of functions already known. End footnote. The solution often seems as different from the original expression as a butterfly does from the caterpillar that it was. Who would have supposed that such an innocent thing as dy/dx equals 1/a² minus x² could blossom into y equals 1/2a log base e a add x over a minus x add c, yet the latter is the solution of the former. As a last example, let us work out the above together. By partial fractions, 1/a² minus x² equals 1/2a open bracket a add x close bracket add 1/2a open bracket a minus x close bracket. dy equals dx over 2a open brackets a add x close bracket add dx over 2a open brackets a minus x close bracket. Y equals 1/2a open bracket integral dx over a add x add integral dx over a minus x close bracket equals 1/2a open brackets log base e open brackets a add x close bracket minus log base e open brackets a minus x close bracket equals 1/2a log base e a add x over a minus x add c. Not a very difficult metamorphosis. There are whole treatises, such as Boole's Differential Equations, devoted to the subject of thus finding the solutions for different original forms. End of section 53. Section 54 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 54. Exercises 19. 1. Find integral square root of a² minus x² dx. Answer. X square root of a² minus x² all over 2 add a² over 2 sin to the power of minus 1 x over a add c. 2. Find integral x log base e x dx. Answer. X squared over 2 open brackets log base e x minus a half close brackets add c. 3. Find integral x to the power of a log base e x dx. Answer. X to the power of a add 1 all over a add 1 open brackets log base ex minus 1 over a add 1 close brackets add c. 4. Find integral e to the power of x cos e to the power of x dx. Answer. Sin e to the power of x add c. 5. Find integral 1 over x cos open brackets log base ex close brackets dx. Answer. Sin open brackets log base ex close brackets add c. 6. Find integral x squared e to the power of x dx. Answer. E to the power of x open brackets x squared minus 2x add 2 close brackets add c. 7. Find integral open brackets log base ex close brackets to the power of a all over x dx. Answer. 1 over a add 1 open brackets log base ex close brackets to the power of a add 1 add c. 8. Find integral dx over x log base ex. Answer. Log base e open brackets log base ex close brackets add c. 9. Find integral 5x add 1 all over x squared add x minus 2 dx. Answer. 2 log base e open brackets x minus 1 close brackets add 3 log base c open brackets x add 2 close brackets add c. 10. Find integral open brackets x squared minus 3 close brackets dx all over x cubed minus 7x add 6. Answer. Half log base e open brackets x minus 1 close brackets add 1/5 log base e open brackets x minus 2 close brackets add 3/10 log base e open brackets x add 3 close brackets add c. 11. Find integral b dx all over x squared minus a squared. Answer. b over 2a log base e x minus a over x add a add c. 12. Find integral 4x dx all over x to the power of 4 minus 1. Answer. Log base e x squared minus 1 over x squared add 1 add c. 13. Find integral dx over 1 minus x to the power of 4. Answer. 1/4 log base e 1 add x over 1 minus x add a half arc tan x add c. 14. Find integral dx over x times the square root of a minus bx squared. Answer. 1 over root a log base e root a minus root a minus bx squared all over x root a. Let 1 over x equals v, then in the result let the square root of v squared minus b over a equal v minus u. You had better differentiate now the answer and work back to the given expression as a check. End of section 54. Section 55 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 21. Finding some Solutions, Part 1. In this chapter, we go to work finding solutions to some important differential equations, using for this purpose the processes shown in the preceding chapters. The beginner, who now knows how easy most of these processes are in themselves, will here begin to realise that integration is an art. As in all arts, so in this, facility can be acquired only by diligent and regular practice.
He who would attain that facility must work out examples and yet more examples, such as are found abundantly in all the regular treatises on the calculus. Our purpose here must be to afford the briefest introduction to serious work. Example 1. Find the solution of the differential equation ay add b dy over dx equals 0. Transposing, we have b dy over dx equals minus ay. Now the mere inspection of this relation tells us that we have got to do with a case in which dy over dx is proportional to y. If we think of the curve which will represent y as a function of x, it will be such that its slope at any point will be proportional to the ordinate at that point, and will be a negative slope if y is positive. So obviously the curve will be a die-away curve, and the solution will contain e to the power of minus x as a factor. But without presuming on this bit of sagacity, let us go to work. As both y and dy occur in the equation and on opposite sides, we can do nothing until we get both y and dy to one side and dx to the other. To do this, we must split our usually inseparable companions dy and dx from one another. dy over y equals minus a over b dx. Having done the deed, we now see that both sides have got into a shape that is integratable, because we recognise dy over y, or 1 over y times dy, as a differential that we have met with when differentiating logarithms, so we may at once write down the instructions to integrate. Integral dy over y equals integral minus a over b dx, and doing the two integrations we have log base ey equals minus a over bx add log base ec, where log base ec is the yet undetermined constant of integration. Footnote. We may write down any form of constant as the constant of integration, and the form log base ec is adopted here by preference, because the other terms in this line of equation are treated as logarithms, and it saves complications afterward if the added constant be of the same kind. End footnote. Then, delogarising, we get y equals c e to the power of minus a over b x, which is the solution required. Now this solution looks quite unlike the original differential equation from which it was constructed, yet to an expert mathematician they both convey the same information as to the way in which y depends on x. Now, as to the c, its meaning depends on the initial value of y. For if we put x equals 0 in order to see what value y then has, we find that this makes y equals c e to the power of minus 0, and as e to the power of minus 0 equals 1, we see that c is nothing else than the particular value of y at starting. Footnote. Compare what was said about the constant of integration with reference to figure 48 on page 184 and figure 51 on page 187. End footnote. This we may call y0, and so write the solution as y equals y0 e to the power of minus a over b x. Example 2. Let us take as an example to solve ay add b dy over dx equals g, where g is a constant. Again, inspecting the equation will suggest 1. That somehow or other e to the power of x will come into the solution, and 2. That if at any point of the curve y becomes either a maximum or a minimum, so that dy over dx equals 0, then y will have the value of g over a. But let us go to work as before, separating the differentials and trying to transform the thing into some integrable shape. b dy over dx equals g minus ay. dy over dx equals a over b, open brackets, g over a minus y, close brackets. dy all over y minus g over a equals minus a over b dx. Now we have done our best to get nothing but y and dy on one side and nothing but dx on the other, but is the result on the left side integrable? It is of the same form as the result on page 145, So writing the instructions to integrate, we have integral dy all over y minus g over a equals minus integral a over b dx. And doing the integration and adding the appropriate constant, log base e, open brackets, y minus g over a, close brackets, equals minus a over bx, add log base ec, whence y minus g over a equals c e to the power of minus a over bx, and finally y equals g over a, add c e to the power of minus a over bx, which is the solution. If the condition is laid down that y equals 0 when x equals 0, we can find c, for then the exponential becomes equals 1, and we have 0 equals g over a add c, c equals minus g over a. Putting in this value, the solution becomes y equals g over a, open brackets, 1 minus e to the power of minus a over b x, close brackets. But further, if f grows indefinitely, y will grow to a maximum, for when x equals infinity, the exponential equals 0, giving y max equals g over a. Substituting this, we get finally y equals y max, open brackets, 1 minus e to the power of minus a over bx, close brackets. This result is also of importance in physical science. Example 3. Let ay add b dy over dt equals g times sin 2 pi nt. We shall find this much less tractable than the preceding. First divide through by b. dy over dt, add a over by, equals g over b times sin 2 pi nt. Now as it stands, the left side is not integratable, but it can be made so by the artifice, and this is where skill and practice suggest a plan of multiplying all the terms by e to the power of a over bt, giving us dy over dt e to the power of a over bt, add a over by e to the power of a over bt equals g over b e to the power of a over bt times sin 2 pi nt, which is the same as dy over dt e to the power of a over bt, add y d open brackets e to the power of a over bt, close brackets, over dt equals g over b e to the power of a over bt times sin 2 pi nt. And this being a perfect differential may be integrated thus, since if u equals y e to the power of a over bt, du over dt equals dy over dt e to the power of a over bt, add y d open brackets e to the power of a over bt, close brackets, over dt. Y equals e to the power of a over bt equals g over b integral e to the power of a over bt times sin 2 pi nt dt, add c, or y equals g over b e to the power of minus a over bt integral e to the power of a over bt times sin 2 pi nt dt, add c e to the power of minus a over bt. Equation A. The last term is obviously a term which will die out as t increases, and may be omitted. The trouble now comes in to find the integral that appears as a factor. To tackle this we resort to the device of integration by parts, the general formula for which is integral u dv equals uv minus integral v du. For this purpose we write u equals e to the power of a over bt and dv equals sin 2 pi nt dt. We shall then have du equals e to the power of a over bt times a over b dt, and b equals minus 1 over 2 pi n cos 2 pi nt. Inserting these, the integral in question becomes integral e to the power of a over bt sin 2 pi nt dt equals minus 1 over 2 pi n times e to the power of a over bt times cos 2 pi nt minus integral minus 1 over 2 pi n cos 2 pi nt times e to the power of a over bt times a over b dt equals minus 1 over 2 pi n times e to the a over bt cos 2 pi nt add a over 2 pi nb integral e to the power of a over b t times cos 2 pi nt dt. Equation b. The last integral is still irreducible. To evade the difficulty, repeat the integration by parts of the left side, but treating it in the reverse way by writing u equals sin 2 pi nt and dv equals e to the power of a over bt dt, whence du equals 2 pi n times cos 2 pi nt times dt, and v equals b over a e to the power of a over bt. Inserting these, we get integral e to the power of a over bt times sin 2 pi nt dt equals b over a times e to the power of a over bt times sin 2 pi nt minus 2 pi nb all over a integral e to the power of a over bt times cos 2 pi nt dt. Equation c. Noting that the final intractable integral in c is the same as that in b, we may eliminate it by multiplying b by 2 pi nb all over a and multiplying c by a over 2 pi nb and adding them. The result, when cleared down, is integral e to the power of a over bt times sin 2 pi nt dt equals e to the power of a over bt open brackets ab sin 2 pi nt minus 2 pi nb squared cos 2 pi nt all over a squared add 4 pi squared n squared b squared close brackets. Inserting this value in a, we get y equals g open brackets a sin 2 pi nt minus 2 pi nb cos 2 pi nt all over a squared add 4 pi squared n squared b squared close brackets. To simplify still further, let us imagine an angle phi such that tan phi equals 2 pi nb over a. Then sin phi equals 2 pi nb all over the square root of a squared add 4 pi squared n squared b squared, and cos phi equals a over the square root of a squared add 4 pi squared n squared b squared. Substituting these, we get y equals g cos phi sin 2 pi nt minus sin phi cos 2 pi nt all over the square root of a squared add 4 pi squared n squared b squared, which may be written y equals g sin open brackets 2 pi nt minus phi close brackets all over the square root of a squared add 4 pi squared n squared b squared, which is the solution desired. This is indeed none other than the equation of an alternating electric current, where g represents the amplitude of the electromotive force, n the frequency, a the resistance, b the coefficient of self-induction of the circuit, and phi is an angle of lag. End of section 55. Section 56 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 21, Finding Some Solutions, Part 2. Example 4. Suppose that m dx add n dy equals 0. We could integrate this expression directly if m were a function of x only and n a function of y only, but If both m and n are functions that depend on both x and y, how are we to integrate it? Is it itself an exact differential? That is, have m and n each been formed by partial differentiation from some common function u or not? If they have, then delta u over delta x equals m and delta u over delta y equals n. And if such a common function exists, then delta u over delta x dx add delta u over delta y dy is an exact differential. Now the test of the matter is this. If the expression is an exact differential, it must be true that dm over dy equals dn over dx, for then d open brackets du close brackets all over dx dy equals d open brackets du close brackets over dy dx, which is necessarily true. Take as an illustration the equation open brackets 1 add 3xy close brackets dx add x squared dy equals 0. Is this an exact differential or not? Apply the test. D open brackets 1 add 3xy close brackets over dy equals 3x, and d open brackets x squared close brackets over dx equals 2x, which do not agree. Therefore it is not an exact differential, and the two functions 1 add 3xy and x squared have not come from a common original function. Is it possible in such cases to discover, however, an integrating factor, that is to say, a factor such that if both are multiplied by this factor, the expression will become an exact differential? There is no one rule for discovering such an integrating factor, but experience will usually suggest one. In the present instance, 2x will act as such. Multiplying by 2x we get open brackets 2x add 6x squared y close brackets dx add 2x cubed dy equals 0. Now apply the test to this. D open brackets 2x add 6x squared y close brackets over dy equals 6x squared. D open brackets 2x cubed close brackets over dx equals 6x squared, which agrees. Hence this is an exact differential and may be integrated. Now, if w equals 2x cubed y, dw equals 6x squared y dx add 2x cubed dy, hence integral 6x squared y dx add integral 2x cubed dy equals w equals 2x cubed y, so that we get u equals x squared add 2x cubed y add c. Example 5. Let d2y over dt squared add n squared y equals 0. In this case we have a differential equation of the second degree in which y appears in the form of a second differential coefficient as well as in person. Transposing, we have d2y over dt squared equals minus n squared y. It appears from this that we have to do with a function such that its second differential coefficient is proportional to itself, but with reversed sign. In chapter 15 we found that there was such a function, namely the sine, or the cosine also, which possessed this property. So, without further ado, we may infer that the solution will be of the form y equals a sin open brackets pt add q close brackets. However, let us go to work. Multiply both sides of the original equation by 2 dy over dt and integrate, giving us 2 d2y over dt squared dy over dt add 2x squared y dy over dt equals 0, and us 2 d2y over dt squared dy over dt equals d open brackets dy over dt close brackets squared over dt open brackets dy over dt close brackets squared add n squared open brackets y squared minus c squared close brackets equals 0, c being a constant. Then, taking the square roots, dy over dt equals minus n square root of y squared minus c squared, and dy over the square root of c squared minus y squared equals n dt. But it can be shown that 1 over the square root of c squared minus y squared equals d open brackets, arc sin y over c, close brackets, over dy, whence, passing from angles to sines, arc sin y over c equals nt add c1, and y equals c sin open brackets nt add c1, close brackets, where c1 is a constant angle that comes in by integration, or preferably this may be written y equals a sin nt add b cos nt, which is the solution. Example 6. d2y over dt squared minus n squared y equals 0. Here we obviously have to deal with a function y which is such that its second differential coefficient is proportional to itself. The only function we know that has this property is the exponential function, and we may be certain therefore that the solution of the equation will be of that form. Proceeding as before, by multiplying through by 2 dy over dx, and integrating, we get 2 d2y over dx squared dy over dx minus 2x squared y dy over dx equals 0, and as 2 d2y over dx squared dy over dx equals d open brackets dy over dx close brackets squared over dx, open brackets dy over dx close brackets squared minus n squared open brackets y squared add c squared close brackets equals 0, dy over dx minus n square root of y squared add c squared equals 0, where c is a constant, and dy over the square root of y squared add c squared equals n dx. Now, if w equals log base e open brackets y add the square root of y squared add c squared close brackets equals log base e u, dw over du equals 1 over u. du over dy equals 1 add y over the square root of y squared add c squared equals y add square root of y squared add c squared all over the square root of y squared add c squared, and dw over dy equals 1 over the square root of y squared add c squared. Hence, integrating, this gives us log base e open brackets y add square root of y squared add c squared close brackets equals nx add log base e big C. Y add square root of y squared add c squared equals big C e to the power of nx, equation 1. Now, open brackets, y add square root of y squared add c squared close brackets times open brackets minus y add square root of y squared add c squared close brackets equals c squared. Whence, minus y add square root of y squared add c squared equals c squared over big C e to the power of minus nx, equation 2. Subtracting equation 2 from equation 1 and dividing by 2, we then have y equals half big C e to the power of nx minus a half c squared over big C e to the power of minus nx, which is more conveniently written y equals a e to the power of nx add b e to the power of minus nx, or the solution, which at first sight does not look as if it had anything to do with the original equation, shows that y consists of two terms, one of which grows logarithmically as x increases, and of a second term which dies away as x increases. Example 7. Let b d2y over dt squared add a dy over dt add gy equals 0. Examination of this expression will show that, if b equals 0, it has the form of example 1, the solution of which was a negative exponential. On the other hand, if a equals 0, its form becomes the same as that of example 6, the solution of which is the sum of a positive and a negative exponential. It is therefore not very surprising to find that the solution of the present example is y equals open brackets e to the power of minus mt close brackets open brackets a e to the power of nt add b e to the power of minus nt close brackets, where m equals a over 2b and n equals the square root of a squared over 4b squared minus g over b. The steps by which this solution is reached are not given here, they may be found in advanced treatises. Example 8. d2y over dt squared equals a squared d2y over dx squared. It was seen that this equation was derived from the original, y equals big F as a function of x add at, add little f as a function of x minus at, where big F and little f were any arbitrary functions of t. Another way of dealing with it is to transform it by a change of variables into d2y over du dv equals 0, where u equals x add at and v equals x minus at, leading to the same general solution. If we consider a case in which big F vanishes, then we have simply y equals little f as a function of x minus at, and this merely states that at the time t equals 0, y is a particular function of x and may be looked upon as denoting that the curve of the relation of y to x has a particular shape. Then any change in the value of t is equivalent simply to an alteration in the origin from which x is reckoned. That is to say, it indicates that, the form of the function being conserved, it is propagated along the x direction with a uniform velocity a, so that whatever the value of the ordinate y at any particular time t0, at any particular point x0, the same value of y will appear at the subsequent time t1 at a point further along, the abscissa of which is x0 add a open brackets t1 minus t0 close brackets. In this case, the simplified equation represents the propagation of a wave, of any form, at a uniform speed along the x direction. If the differential equation had been written m d2y over dt squared equals k d2y over dx squared, the solution would have been the same, but with the velocity of propagation would have the value a equals the square root of k over m. You have now been personally conducted over the frontiers into the enchanted land, and in order that you may have a handy reference to the principal results, the author, in bidding you farewell, begs to present you with a passport in the shape of a convenient collection of standard forms. In the middle column are set down a number of the functions which most commonly occur. The results of differentiating them are set down on the left, the results of integrating them are set down on the right. May you find them useful. End of section 56.
Section 57 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rachel. Calculus Made Easy by Silvanus P. Thompson. Epilogue and Apologue. It may be confidently assumed that when this tractate, Calculus Made Easy, falls into the hands of the professional mathematicians, they will, if not too lazy, rise up as one man and damn it as being a thoroughly bad book. Of that there can be, from their point of view, no possible manner of doubt whatever. It commits several most grievous and deplorable errors. First, it shows how ridiculously easy most of the operations of the calculus really are. Secondly, it gives away so many trade secrets. By showing you that, what one fool can do, other fools can do also, it lets you see that these mathematical swells, who pride themselves on having mastered such an awfully difficult subject as the calculus, have no such great reason to be puffed up. They like you to think how terribly difficult it is, and don't want that superstition to be rudely dissipated. Thirdly, among the dreadful things they will say about "so easy," is this, that there is an utter failure on the part of the author to demonstrate with rigid and satisfactory completeness the validity of sundry methods which he has presented in simple fashion, and has even dared to use in solving problems. But why should he not? You don't forbid the use of a watch to every person who does not know how to make one. You don't object to the musician playing on a violin that he has not himself constructed. You don't teach the rules of syntax to children until they have already become fluent in the use of speech. It would be equally absurd to require general rigid demonstrations to be expounded to beginners in the calculus. One other thing will the professed mathematicians say about this thoroughly bad and vicious book, that the reason why it is so easy is because the author has left out all the things that are really difficult. And the ghastly fact about this accusation is that it is true. That is indeed why the book has been written for the legion of innocents who have hitherto been deterred from acquiring the elements of the calculus by the stupid way in which its teaching is almost always presented. Any subject can be made repulsive by presenting it bristling with difficulties. The aim of this book is to enable beginners to learn its language, to acquire familiarity with its endearing simplicities, and to grasp its powerful methods of solving problems, without being compelled to toil through the intricate, out of the way, and mostly irrelevant, mathematical gymnastics so dear to the unpractical mathematician. There are amongst young engineers a number on whose ears the adage that "what one fool can do another can" may fall with a familiar sound. They are earnestly requested not to give the author away, nor to tell the mathematicians what a fool he really is. End of Section 57. End of Calculus Made Easy by Silvanus P. Thompson.